Okay, hello everyone. This is module 12 of Econometric Modelling. This also deals with multiple regression analysis. So, in the previous module I just briefly introduced certain concepts related to multiple regression. Specifically what we talked about was the how do we arrive at or derive the estimated parameters, and then we talked about assumptions and properties, important properties of the estimated parameters. Now, we will give you the geometric interpretation followed by one important theorem and its application in deriving the residual variance. So, this is while talking about geometric interpretation, we by now know that y hat measures the proportion of y into the column space of x, that is what percentage of y is explained by the independent variables, or maybe whatever portion, the part of y that is being explained by the independent variables. So, these are the column space of the independent variables, and suppose independent variables together explain y. So, this is my y hat, but these are actual observations of y. So, what remains is basically u hat or unobserved, not maybe, rather the residuals. So, error is you can see that the error or the residuals are orthogonal to the entire space. So, orthogonal to the individual vectors. Therefore, if we drop a perpendicular from y on the column space to minimize the residue, then u hat must be the perpendicular distance, because you can see that u hat is perpendicular to the column space, and this also implies that u hat is independent of the column space or individual independent variables. So, this is how we interpret the multiple regression analysis. Of course, when you work with n variables, then it is very difficult to explain an n dimension graph or explaining the n variable regression analysis geometrically or graphically. So, we work with at the max 2 variables, and that too excluding say the constant term. So, what we here try to do is to minimize this orthogonal distance, right, while trying to explain y using various combinations of the x's. There are two projection matrices. Now, we introduced these two projection matrices in order to explain certain concepts and also in order to prove certain theories. So, first of all, the theory that will be coming up next, it will be using these matrices extensively. So, the two matrices, first one is a projection matrix. So, you can see that this is the matrix which gives us the value of y hat, right, because y hat is the projected values of y by the combinations of x's. So, projection matrix gives us the value of y hat. So, the way we construct the projection matrix denoted by Px, which is x into x prime x inverse x prime, it projects any vector y into the column space of x's such that Pxy is equal to x beta hat, and you know x beta hat is actually equal to y hat. Okay. So, when Px multiplied by y, then we get the projected values of y, that is y hat, and that is why Px is called the projection matrix. The other matrix is Mx. This is actually, this gives a vector orthogonal to the column space, because when Mx is multiplied by y, then you can see that by putting the values of y or rather by multiplying this expression, which is I minus x into x prime x inverse x prime, alternatively Mx is defined as I minus Px. This is a matrix which gives a vector orthogonal to the column space. So, you can see that this gives us y minus x beta hat, which is equal to E hat, right. This is because Mx is equals to 0. If you multiply Mx with x, then you will be having x minus x into x prime x inverse x prime x. So, x prime x and x prime x inverse, they cancel out, and I am left with x minus x. So, mx is equals to 0. mx x is equals to x minus x into x prime x inverse x prime x. These two cancels out and then these two cancels out. So, that is how 0, right. So, mx y gives us u hat, and since mx x is equals to 0, we can say that this gives a vector which is orthogonal to the column space, and u hat are all basically orthogonal to the column space. It implies that if y lies completely in the column space of x, then we can always predict that y equals y hat equals x beta hat, which implies u hat equals to 0 and r square equals 1. That is, if y is completely explained by the column space, then what would happen? What would happen is that there will be no orthogonal distance. So, if there is no orthogonal distance between y hat and y, this means u hat is 0. There is no residual. It is completely explained by the combination of the independent variables, and as a result of which the r square as a goodness of fit measure that we had discussed earlier will be equal to 1. That is, the explained sum of square is exactly equal to the total sum of square. So, we have ESS upon TSS equal to 1. Okay. Now, we talk about certain properties of the projection matrices, because again that will be useful. Px is a symmetric matrix, which implies that Px prime is equal to Px. Now, the proofs are also given here. You can see that Px prime is actually Px then prime, that is the transpose is taken, and if I break the transpose, then we actually arrive at Px again. So, that is why we call it Px. Px is a symmetric matrix. Similarly, Mx is also a symmetric matrix, because simply Mx is I minus Px prime. So, I minus Px prime will also be I minus Px, and that is equal to Px. Px and Mx are idempotent matrix, that is, if I multiply Px with Px or Px square, then again we arrive at Px. Similarly, Mx into Mx is actually equal to Mx, and the proofs are also given here, right. So, these are the two very important properties of the projection matrices. First, they are symmetric matrices, second, they are idempotent matrices. Now, we talk about a theorem which is Frisch-Waugh-Lovell theorem. It was given by these econometricians. In the linear least square regression of vector y on two sets of variables x1 and x2, the theorem states that the subvector beta 2 hat is the set of coefficients obtained when the residuals from a regression of y on x1 alone are regressed on the set of residuals obtained when each column of x2 is regressed on x1. So, the theorem states that by regressing y on a set of independent variables and obtaining the residuals, again we regress the rest of the independent variables on the first set of independent variables, retain the residuals, and now if I regress the first residual on the second set of residuals, then we arrive at, or we can derive the parameter estimates of the second set of independent variables, right. Okay. So, the matter appears a little complex, that is actually explained, and this theorem is also proved in the subsequent slides. So, we divide the regressors into two groups K1 and K2, such that K1 plus K2 is equal to the total number of independent variables, which is K. So, we write it as y equals x1 beta 1 hat plus x2 beta 2 hat plus u hat, right. If we had regressed y on x1 and then x2, then we would have arrived at this expression in the sample, right. Now, here the dimensions of y and x1, x2 and beta 1, beta 2 hat are mentioned. So, y is a n by 1 vector as usual, x1 is n by k1, x2 is n by k2, beta 1 hat k1 by 1, beta 2 hat k2 by 1, and u hat is again n by 1. Now, the Frisch-Waugh-Lovell theorem uses of course these matrices. So, first of all, let me show you that mx1 y is equal to mx1 x2 beta 2 hat plus u hat. Why this is so? Because I have just mentioned that y is actually x1 beta 1 hat plus x2 beta 2 hat plus u hat. So, given that y is x1 beta 1 hat plus x2 beta 2 hat plus u hat, mx1 y, and then replacing the values of y into this expression, I will be having mx1 x1 beta 1 hat plus mx1 x2 beta 2 hat plus mx1 u hat, right. And then since mx1 x1 is equals to 0, if you remember the way we defined mx, we proved that mxx is equal to 0. So, in a similar fashion we are defining mx1, so mx1 x1 will also be 0. So, since mx1 x1 is actually equal to 0, I am left with mx1 x2 beta 2 hat plus u hat. Okay. Now, x2, now I am multiplying this expression with x2 prime. So, multiplying this with x2 prime, I have x2 prime mx1 x2 beta 2 hat plus x2 prime u hat, but x2 prime u hat is equals to 0 because u hat, the residuals are independent of all functional forms of x, that is all the independent variables. So, x2 prime u hat will be equal to 0, as a result of which I have only this expression, right, which implies that beta 2 hat will be basically this thing inverse multiplied by x2 prime mx1 y. So, I have x2 prime mx1 x2 inverse x2 prime mx1 y. Okay. Now, mx1 x2 is the residuals from regression of x2 on columns of x1. If you remember, mx y was equal to ut hat or u hat, which implies that when we are regressing y on x and then multiplying mx with y, then we are arriving at the residuals obtained from the regression of y on x. So, mx1 x2 must be giving us the regression or the residuals from the regression of x2 on x1, right. So, that is what is mentioned here, that mx1 x2 is the residuals from regression of x2 on the columns of x1, and mx1 y in a similar fashion is the residuals from regression of y on the columns of x1. So, if we run a regression of mx1 y on mx1 x2, that would also result in beta 2 hat equals to this. See, now I draw analogy with beta hat, which is x prime x inverse x prime y. Now, here my x is mx1 x2, that is we are running a regression of mx1 y on mx1 x2. So, mx1 x2 is my x here. So, I will be having mx1 x2 prime, which is mx1 x2 prime. Since mx1 prime and mx are the same, they are symmetric matrix. So, that is why mentioning a prime or not mentioning it are the same thing. So, I have x prime, which is x2 prime mx1 prime x mx1 x2 inverse x2 prime mx1 prime mx1 y, right. So, that is equivalent to our x prime x inverse x prime y. Since mx1 prime mx1 equals to mx1 mx1 is equal to mx1 because they are idempotent matrices. So, I have x2 prime mx1 x2 inverse x2 prime mx1 y, since mx1 is an idempotent matrix. So, this proves that beta 2 hat can be obtained from the regression of the residuals of a regression of x1 on y on the residuals from a regression of x2 on x1. Okay. So, what are the steps involved in Frisch-Waugh-Lovell theorem? First of all, I regress x2 on x1 and collect the residuals mx1 x2. then I regress y on x1 and collect the residuals mx1 y, and after that we regress mx1 y, that is this residuals, on mx1 x2, that is these residuals, to obtain beta 2 hat. So, we are not, see, we could have obtained beta 2 hat directly by regressing y on x1 and x2 separately, right. But Frisch-Waugh-Lovell theorem says that if I follow these procedures also, then we are going to exactly arrive at the same set of estimates that would have been given by this kind of a regression, right. So, this is the theorem. Now, it has certainly its applications and usefulness, that is why the theorem has been developed. So, a theoretical application will be discussed very soon, while we actually try to derive the residual variance. Now, first of all, why residual variance would be different from the population error variance. So, what I am trying to claim here is that the population error variance is actually not equal to the variance of the residual, and first of all that is explained here, that why it is so. The errors are never observable, while the residuals are computed from data. The residuals can be written as a function of the errors as ui hat equals yi minus beta naught hat minus beta 1 hat xi, right. So, now look at here that I am actually working with a simple regression model, that is I have a constant term and I have only one variable here. Now, this is actually equal to, you can see that yi can be further replaced with its population expression or model. So, beta naught plus beta 1 xi plus ui minus beta naught hat minus beta 1 hat xi. So, ui hat is actually ui coming here, and then I am collecting these terms beta naught and beta naught hat. So, this is collected here, and beta 1 xi and beta 1 xi hat, they are collected here, right. So, this shows that although the expected value of beta naught hat and beta 1 hat are supposed to be beta naught and beta 1 respectively, ut hat is not the same as ut, right. So, or ui hat is not the same as ui. See, the long I do not take an expected value here. So, I am actually not saying that these are the same thing. So, individually they can be different, the population error can be very different from the sample residual. So, given that sigma square is the population variance, that is, this is equal to expected value of u square. Alternatively, it can be written as summation ui square divided by n, or n raised to the power minus 1 summation ui square, but this is not equal to summation ui hat square divided by n, since ui hat and ui, they are not the same thing. So, sigma square equals n raised to the power minus 1 summation ui hat square is a biased estimator of the population error variance, right. Now, I further discuss that why it is a biased estimator. First of all, we have shown that they are not the same thing. So, by dividing them by n, we certainly not get the same thing, right. That itself indicates that this is not the right estimator of this. The unbiased estimator of the population error variance is actually u hat prime u hat divided by n minus 2 for 2 variable case, and consequently this is u hat prime minus u hat divided by n minus k for k variable case, or in case I have k plus 1 variable, then this will be n minus k minus 1. This is because the value of u hat is obtained by choosing values of alpha hat and beta hat that minimizes the two first order conditions for 2 variables case, and in case we have k plus 1 variables, then there will be k plus 1 first order conditions. Thus, there are only n minus 2 degrees of freedom in the OLS residuals as opposed to n degrees of freedom in the errors. So, when we talk about degrees of freedom, what it actually implies? In case the population error actually can, if I consider n observations, then the population error can be any n observations, right. But what happens is that when it comes to sample residuals, we are choosing alpha and beta in order to minimize the values of the sample squared sum of the sample residuals. So, as a result of which it says that since there are two first order conditions, the sample residuals can actually take n minus 2 observations or 2 n minus 2 free observations. So, I mean I give a simplistic example of the concept of degrees of freedom. Suppose I there are, I say that there are 10 observations of the variable x. So, the variable x takes 10 observations and I do not specify what are the observations, but I only specify that these 10 observations add up to a number say 100. So, I can take up any numbers below 100, so that these numbers add up to 100, fair enough. But if I specify 2 observations, this is a case where there are 10 degrees of freedom. I can take any 10 numbers, those who add up to 100, but in case I specify 2 numbers. So, suppose I specify that x 1 is equal to 8 and x 2 is equal to 18, then the rest of the 8 numbers have to adjust itself accordingly, so that the total sum is actually 8 plus 18, that is 100 minus 26, fair enough. So, now you can see that I have imposed 2 conditions, and that is why 2 degrees of freedoms are reduced. Now, the degrees of freedom is actually equal to 10 minus 2, that is 8. There are only 8 observations who are, or 8 observations who are free to take any number which add up to 100 minus 26, right. So, in a similar fashion, because there are 2 constraints imposed, that is while choosing alpha hat and beta hat, that reduces the degrees of freedom for the sample residuals by n minus 2. Otherwise, there had been n observations or n degrees of freedom for the sample residuals as well, unless or if we had not followed the procedure of OLS, right. So, alternatively, since OLS minimizes the sum of squared residuals, of course, this is a deliberate attempt to make it the smallest possible, as a result of which summation ut hat squares or u hat square must be less than equal to summation u square, that is their population counterpart. Hence, summation u hat square divided by n should be less than equal to summation u square by n. Summation u square by n is the true and unbiased estimator of sigma. Therefore, summation u hat square by n has to be a biased estimator. We need to reduce the denominator, because this is something which is fixed. So, we can actually only change the denominator. So, we can reduce the denominator in order to make the entire expression going up, so that now this is less than equal to, it becomes equal to, it goes up, it becomes equal to summation u square by n. Okay. So, you need to reduce the denominator or divide summation u hat square by a number less than n to bring equality in 1, or convert summation u hat square by n into an unbiased estimator. So, the Frisch-Waugh-Lovell theorem is a useful tool to obtain this. By now, I explain the application of Frisch-Waugh-Lovell theorem. So, while discussing it, I first use another concept, which is the trace of a matrix. So, the trace of a matrix is the sum of its diagonal elements, right. So, this is a matrix, the sum of its diagonal elements are called the trace. Properties of trace which are going to be used here are also discussed here. First of all, trace A plus B equals trace A plus trace B, and trace A B C are all different matrices, is equal to trace B C A equals trace C A B, right. Now, we know that u hat is equal to mxy, right. Now, mxy is equal to mxu also, because y is equal to x beta plus u, and mxx is equals to 0. So, x beta multiplied by mx becomes 0, I am left with mxu. Now, we see that u hat prime u hat is actually equal to u prime mx u, okay, because mx square is equal to mx and mx prime equals to mx. Because of this, you know, as mx is a symmetric matrix as well as idempotent matrix, we can write it like this. So, u hat prime multiplied by u is mx u prime multiplied by mx u. So, u prime mx mx u is u prime mx u. Now, expected value of u hat prime u hat is expected value of this expression. Now, you can see that this is a 1 by n matrix, mx is an n by n matrix and u is a n by 1 matrix. So, this is a number. Since this is a number, I can always, you know, write trace of u prime mx u and before the expected value. So, a number's trace is basically the number itself. But now, since applying this, you know, property of the trace of a matrix, I can always write it as mx u u prime. Trace u prime mx u is equal to trace mx u u prime. Now, this is not a 1 by 1 matrix. This is actually a n by n matrix now. This is n by n, right. Now, I take the trace operator outside and expectation goes inside, and this is actually non-random given that they are conditional, given that this is you know, depends only on the values of x and conditional upon x. So, mx is non-random, mx comes out, expected value of u hat is sigma square I n, that has already been proved. So, sigma square being a constant, it actually comes out. So, I am left with trace of mx, mx I is actually mx because I is an identity matrix. So, sigma square trace mx. Now, trace mx is I expand or input the value of mx, the trace of the matrix I will be n, and then trace of this matrix, rearranging terms I arrive at trace of this matrix as k. So, trace of mx is actually n minus k. Now, you remember I had expected value of u hat prime u hat is equal to sigma square trace of mx. Trace of mx is n minus k. So, I replace it with n minus k, which implies that expected value of u hat prime u hat divided by n minus k is equal to sigma square. So, this shows that this is an unbiased estimator of sigma square and not n. So, I am not going to divide u hat prime by u hat by only n in order to arrive at an unbiased estimator of the population variance. I need to divide it by n minus k if there are k variables in the regression. If there are 2 variables, then it should be n minus 2 and so on. Okay. And then finally, we talk about the assumption of normality that has already been actually discussed in the case of or in the context of simple regression analysis, that CLRM, that is classical linear regression model assumptions, include the assumption of normality beside the 5 assumptions of the Gauss-Markov theorem. This assumption states that the population error u is independent of the explanatory variables x1 to xk and is normally distributed with mean 0 and variance sigma square. So, u is normally distributed with 0 mean and sigma square as its variance. Alternatively, it can also be written as y follows conditional upon the values of x, a normal distribution with mean beta naught plus beta 1 x1 plus beta 2 x2 and so on, and sigma square as the variance. Now, if you remember that I just need to mention here that in case of Gauss-Markov theorem, we had or we have an additional assumption, that is the assumption of no perfect collinearity between or among the independent variables. This assumption was not relevant in the case of simple regression model because we had only one independent variable. Since in case of multiple regression analysis, we have multiple independent variables. So, this assumption has been brought into, that is an additional assumption we have for multiple regression analysis under the Gauss-Markov theorem. But this assumption was actually very much a part of the simple regression analysis as well. So, from here we also derive the sampling distribution, that is normality of the error terms translate into normal sampling distributions of the OLS estimators, that is beta j hat is also normally distributed with beta j as the mean and variance of beta j hat as the variance, or alternatively we can write that beta j hat minus beta j divided by the standard deviation. Ideally it should be the standard error of beta j hat normally distributed with mean 0 and variance 1. This is comes straight away from the fact that expected value of beta hat is equal to beta, that is the unbiasedness. Thus, beta hat or beta j hat is a linear combination of the errors in the sample. X is non-random, that is given that x is non-random, beta hat or beta j hat is a linear combination of the errors in the sample. An important fact about independent normal random variables is that a linear combination of such random variables is normally distributed. Consequently, beta hat or beta j hat is also normally distributed, right. So, that brings me to the end of some of the discussions on multiple regression analysis. We will further continue with some other topics on multiple regression analysis in the next module. You can follow these books for the discussion that I had so far. Thank you.